So now we're actually ready to start talking about the derivative. And in order to do that, we're going to start by thinking about what we talked about as average rate of change and moving to instantaneous rate of change. At the same time, we're talking about on the graph, looking at secant lines becoming tangent lines. Now, we said that a secant line is just when you connect 2 points on a curve, and we alluded to the fact that a tangent line only touches the curve at one point, at least locally. But we need a little something better for a tangent line. So we can actually define it using these ideas, and then we'll make our way to the derivative. So let's take a look at this graph here. Let's call this f of x. Okay, and so we have 2 points, A, so this would actually be A, f of A, and then a point that is h away. So this distance here is just h. So what we're doing is, instead of looking at it as 2 separate points like we did last time with, say, x0 and x1, we're looking more based at the point A and then h away from A. So we're just refocusing it at one point. Okay, so this would be A plus h, comma, f of A plus h. All right, so if we want to look at the secant line, that was just this. Remember? That was the secant line. All right, so the idea that we'd mentioned earlier was that this now gives us average rate of change, slope of the secant line, that sort of thing. But what we want to do is transition to the point A itself without the A plus h. So what we want to do is essentially take h to go to 0. So taking h to go to 0 is going to take the A plus h point and move it back towards A. In the same manner, it's basically going to put points on the curve that head towards A. And we'd essentially be looking at different secant lines each time. All right, and our hope is that by doing this, we would get to what would be the tangent line right here. Okay, so if you notice, what if we actually calculated the secant, the slope of the secant? All right, the slope of the secant would be f of A plus h minus f of A over A plus h minus A, or in other words, f of A plus h minus f of A over h. So that's just rewriting it, and that was one of the forms we had mentioned. So there's a form for the secant line, or the average rate of change. And so what we're going to do is we're going to take that in the limit as h approaches 0. And what we're going to get is, in fact, a way to define the tangent line. So let's take a look. So for this definition, we're really defining the tangent line. So if f is defined on an open interval containing a, and if the limit as h approaches 0 of f of A plus h minus f of A over h equals m exists, so if it does exist, then it has a value, and that's what we're calling m, in this case, for a good reason, then the line passing through A f of A with slope m is the tangent line to the graph of f at the point A f of A. And so that is actually what we've denoted there. The line passing through A f of A and has slope m. Okay? So that's what we're getting. So let's take a look. Oh, first let me mention that because we really want to end up talking about the original function, the original curve, we do have a convention of, if we want to talk about the slope of a graph or a slope of a function, we actually use whatever the slope of the tangent line at that point is. So we use that interchangeably. So when we say a slope of a graph, we mean the slope of the tangent line of that graph at that point. Okay, so that's great. As a tangent line, where does this connect with the rates of change, and how do we get to the derivative? Well, all of this is happening. We have three things here that are equivalent, and these are three important ways that we've been looking at this. So the first is, we mentioned rates of change. So the average rate of change that we looked at initially, when you take the limit as h approaches 0, becomes the instantaneous rate of change. Okay. The slope of the secant line connecting 2 points, when you take the limit as h goes to 0, becomes the slope of the tangent line at a single point. And that quantity that we used to calculate the average rate of change, we can know this as the difference quotient. Makes sense because it's actually a quotient of two differences. If you think of the first as the numerator as the differences in the function, and the h as the differences in the x value. So when you take the difference quotient and take the limit as h approaches 0, you get the quantity that we described above, which became the slope of the tangent line, but that is indeed what we're going to call the derivative at the point. So what we're getting, that value we're getting, is what's called the derivative, which corresponds to the slope of the tangent line at that point and the instantaneous rate of change at that point. All right. Now, the only thing that's a bit of a drawback is the way we phrased it is entirely looking at one point, the point A. Okay? So that's just the way we phrased it right now. So our hope is to be able to open this up and talk about it at any point x on the graph of a function. So that's where we want to transition from just looking at a one point to looking at another point, or any point.